Okay, good morning, everybody. Welcome to the second day of the FQ conference. And well, it is my pleasure to introduce for you today our plenary speaker, Felipe Volok, who is going to talk about CAPSAT constructions. So, Felipe, the stage is yours.
Thank you. Okay, thank you very much for the invitation. It's a pleasure to be here, especially being in Brazil, and it's a nice opportunity to give a talk at Fq16. So I'm going to talk about CAPSAT constructions. So this talk is going to be sort of maybe a simple talk. I'm going to present some ideas and prove a couple of results, which are not very deep, but they're maybe very interesting, but they suggest a lot of problems. So this is a talk that hopefully there'll be lots of open problems that I'm going to mention, and I hope that some of you might give me some answers. I've been thinking about this, not for very long, for a few months, from the late last year, and there's all sorts of interesting questions and things. So, okay, so let's get started. So this is the abstract that I submitted. It's not very... And this is the outline of the talk. I'll give an introduction to the notion of CAPSATs, and then I'm going to talk about three different categories of CAPSATs: small complete CAPSATs, greedy CAPSATs, and CAPSATs coming from quadrics. So on the introduction, I'll give you the precise definition. So, okay. So I'm going to be working with the n-dimensional vector space over F3. And your first question is, why 3? The answer is because mod 3, minus 1 is equal to 2. And I'll come back to that in a little while. CAPSATs, well, this is notion of cap, which is very old, and I'll come back to talk about the notion of cap for general affine and projective spaces. But the specific case of F3 to the n has seemed to attracted a lot of attention. Maybe 10 or 15 years ago, Terry Tao said that this is a very interesting problem of large CAPSATs, and people sort of pay attention to what he says. Recently, there's been some work that was done by Google DeepMind together with some mathematicians, and they used AI to produce large CAPSATs. So it's, I don't know, it's fashionable. So I guess I'm following the trend and talking about CAPSATs. So what is a CAPSAT? Is a subset of F3 to the n containing no 3 points on a line. So lines, lines is affine lines. So it's not lines to the origins, affine lines. And every line has 3 points, right? So a CAPSAT is a set that doesn't contain any line, if you want to say it that way, or there's no 3 points on a line. And so the question is, how big can a CAPSAT, what are the sizes of possible CAPSATs? Of course, if you have a CAPSAT, any subset of the CAPSAT is also a CAPSAT. So that's boring, right? So getting a subset. So the natural question is to look at complete CAPSAT. So a complete CAPSAT is a CAPSAT that is not a subset of a larger one. So it's maximal with respect to inclusion, which doesn't mean that it's maximal with respect to size. So we're going to look at those. So I want to look at complete CAPSATs. So a CAPSAT is something that has no 3 points on a line, and is complete if it's not a subset of a larger CAPSAT. And I want to define this set of real numbers, which is the real number. So maybe I'll write it slightly differently on the board. So I'm interested in the numbers alpha, a real number alpha, such that there are CAPSATs, say Cn, inside of F3 to the n, such that the number of points in Cn is about alpha to the n. And I want that for infinitely many n. So there exists Cn for infinitely many n. Okay, so one example of a CAPSAT is the set. So if you're bored, you can do this exercise. This is a complete CAPSAT. So if you want to do an easy exercise, the set of points with coordinates 0, 0, and 1 is a complete CAPSAT. And so this is the situation where alpha is 2, right? So you get CAPSATs complete cap sets of size 2 to the n. And I want to know for which numbers alpha there's a sequence of exponents n, for which there's a cap set Cn and F2 to the n complete. So there's a complete cap sets which with about alpha to the n points. So you get a subset of the real line, right? And the number 2 belongs to it. And it's not very difficult. It takes a little bit of work, but it's a sort of real analysis work and using Cartesian products, that this set, the set of alphas, this set curly C, is an interval. It's a closed interval contained in this interval. So, of course, you cannot make cap sets bigger than 3 to the n, because 3 to the n is the size of the ambient space. And I'll show that you cannot make it smaller than, if it's complete, smaller than root 3 to the n. So it's like that. And the question is, so what is the set? So, and what cap sets can you produce? I'm going to talk about, so here's my root 3. I'm going to talk about 2. I'm going to talk about 3 to the 2/3 here. And then there's this number, little c, which is the biggest number, the largest cap set. So most of the action in the subject has been here. What's the value of this number? That's the big question that, so there's been this big, important work of Ellenberg and Geisweit that proved that C is at most 2.756. And before their work, we didn't even know that C was less than 3. So was a big breakthrough to show that C was smaller than 3, and they gave a numerical value like that. There are some constructions. Tyrrell, I think, has the record, but then also there's this work from Google DeepMind using AI that generates cap sets in dimension 8, and with these cap sets you can sort of construct by Cartesian products also large cap sets for higher dimensions, and you get some value, lower bound for C. But we don't know what the value of little c is. And that's perhaps the fancy problem that people look at. But I don't want to think about this problem because I have nothing to add. So I'm going to look at some other questions that perhaps I can say something about, and maybe you can say something about. But if you can find the value of C, that would be great. So one question that surprisingly had not been addressed before, as far as I can tell, is the lower bound. So why is the square root of 3 in there? So that's going to be my first topic, is to look at small complete cap sets. So what's the size of the smallest complete cap set? And I'm going to show you that is about 3 to the n over 2. Before I get to that, I want to go back to this idea that you can talk about, and people have studied this for many years, so some of you might work in finite geometry, and the notion of arcs and caps is a classical notion, and you can talk about in an n-dimensional space, you can talk about sets of points with no 3 on a line. And so for us, we're looking at q equals 3, but I also want to look at the following thing. I want to look at, suppose I have 3 equals q equals, the notion of cap set is a notion that only depends on f3 to the n as an abelian group, because 3 points are on a line if they add to 0. Okay, so when n is 3, and I guess that's the interesting part, 3 points are on a line exactly when they add to 0. So the notion of cap set only depends on the structure of f3 to the n as an abelian group. But if you have q equals 3 to the m, and you can look at fq to the k, this is, as an abelian group, this is the same thing as f3 to the mk, right? So if I have objects in here, I can regard them as objects in there. And one easy exercise is that if you have a cap in here, in that sense, so a set of points with no tree on a line, no tree on an FQ line, then I'm going to get a cap set, because the FQ lines contain the F3 lines if Q is a power of 3. So I'm going to do that a bit. So switch between looking at caps in here and cap sets in there. But the converse is not true. So if you have a cap, you get a cap set, but if you have a cap set, you don't necessarily get a cap. One thing that I should mention is that there is a big split if you look at caps in low-dimensional spaces over large finite fields. Is very different from the situation that we're going to be looking at, which is the high-dimensional space over a small finite field. So there's this two directions, right? And for example, there's a huge theory about arcs in the plane. So you can take a large finite field and n equals 2 and look at what's called arcs. So a cap in dimension 2 is called an arc traditionally, and that's been looked at a lot. And there's many interesting results. There are also many interesting open problems. But we're not going to be talking most about that. Okay, so we're going to... before I move on, let me mention that there are, the notion of cap sets has lots of applications. So it turns up in the analysis of matrix multiplication algorithms. I'm not going to say much about that. You can Google. You're going to find lots of information. Encoding theory is obviously, like the notion of cap set is pretty clearly related to questions in coding theory. It also turns up in randomness extractors when you have a weak source of random numbers and you want to amplify, get a better source of random numbers. You can use cap sets to do that. And so Erdős had a problem about what's the largest set of integers between 1 and n with no 3 numbers in an arithmetic progression. And the condition that 3 numbers x, y, and z are in an arithmetic progression is this, right? X, y, and z are in arithmetic progression if this is satisfied. And in characteristic 3, 2 is minus 1. So in characteristic 3, this is the same thing as... So the cap set problem is similar. It's not the same problem, obviously, as the problem in integers. It's a different problem, but it has similarities. And one reason people started looking at cap sets was as a model, right? So what can we say in an easier situation? The Erdős problem, I think. There are some results, but I think we don't know exactly what's the largest subset of this integers between 1 and n for which no 3 in an arithmetic progression. Okay, so let's start talking about small complete cap sets. Here's a easy theorem. Okay, so I'm going to give you a lower bound on the size of a complete cap set. So how do we do that? Suppose you have a cap set with capital N points, and for each pair of points, you can draw the line through the 2 of them, and because it's a cap set, the third point is outside. So for each pair of points on the cap set, you get the point outside. Now, how many points do you get? And then minus 1 over 2, maybe less, because the two lines could meet at the same point, but you get at most that many points. Now, there are capital N points on the cap set, and so this many points, 3 to the little n minus capital N, points outside of the cap set. And if the number of points that you get by taking 2 points and making a line and getting the third point is smaller than this, it means that there is a point among those outside of the cap set that is not on any line through 2 points of the cap set, which means that the cap set is not complete. Okay, so if this inequality is satisfied, the cap set cannot be complete. So a complete cap set satisfies this inequality here, which means that it has at least this many points, which means that this interval, it doesn't have any numbers smaller than square root of 3. Square root of 3 is a lower bound for the size of the elements of curly C. Okay, so but what's the actual size of the smallest cap set? So that's the question I want to start with. So oops, I ruined my joke. So one way to construct cap sets is to get a conic, right? So this is what I talked about. So if you look at and you can take a conic in here, like a parabola. A conic is a cap set, and it has q points. Say if you take y squared, y equals x squared, you get q points, and it's a cap set, but it's too small to be complete because it's q points in fq squared. So it's too small to be complete. But I'm going to show you that you can get a complete cap set by taking two conics. So this is y equals x squared, y equals negative x squared. And if you think of it as a cap in fq squared, this is obviously not a cap. But surprisingly, it is a cap set. So remember, you're just looking at the F3 line, so triples of points adding to 0. So this set here, I have to exclude the origin. So this set here in fq squared is a cap set. That's not too hard to prove. And if you assume that q is an odd power of 3, then you can actually prove that it's complete. Doesn't look like it, but it works. You know, it surprised me when I found this. I wrote this down, and I was trying to do something else, and this came up, and I said, "Well, that can't possibly be true," but it works. So you get this many points, which shows that the minimum is root 3. So the smallest element in the set curly C is the square root of 3. That's the rough size of the smallest cap set, complete cap set, is 3 to the n over 2. However, if you go back to the joke now, to the theorem here, the lower bound is this: square root of 2 times 3 to the n over 2. And the set that I'm constructing has 2 times. So there's a little gap between square root 2 q to a half and 3 to the n over 2 and 2 times 3 to the n over 2. And I do not know what's the exact size of the smallest complete cap set. So this is the first problem that I want to pose to you that comes out of the stuff that I've been doing is, what's the size of the smallest complete cap set? This construction is interesting, and you can extend it. So you have that is complete when m is odd. When m is even, it's not complete. And in fact, you can add more conics. You can add more parabolas. You can add more parabolas of the form y equals c times x squared. And I don't know how many more you can add. So one of my colleagues did the computer search for, I don't know, it was q equals 81 maybe, and or q equals 9, so the whole space is size 81, and found that we could add 4 or 5 conics. So you know, it's an interesting. I mean, it's not going to help you to find large cap sets, I don't think. Maybe it can, but you know, it's the question: so how many of these parabolas can you put together and make a cap set when m is even? So that's another problem that comes out of this construction. Excuse me. Get this drink of water before I can move on to the next. Okay, so So that was, can I point to the lower bound here? Now I want to talk about, so you can get points in the middle just by taking Cartesian products and playing games, but I'd like to construct explicit cap sets which corresponds to alpha equals 2 and alpha equals 3 to the 2/3. So my next topic is going to be this greedy cap sets, which will give me cap sets of this size. So what's a greedy cap set? I thought of the following idea to construct large cap sets, which turned out not to work. Okay, but it's an idea that constructs cap sets. So I start with a whole space, F3 to the n, which is not a cap set because, you know, lots of lines. And I'm going to start throwing away points until I get a cap set. But I want to throw away the points in some systematic way. So what am I going to do? So the first point is just throw away any point, it doesn't matter. But suppose that you, at some stage you threw away some points and you look at the set of remaining points, which may contain some lines still. So you're going to take any point in the set of remaining points and look at the lines contained in the set starting from that point. There may be not any for that point, but there might be 1, there might be 2, there might be 17, I don't know. I count how many lines through this point, which is in my set of remaining points, how many lines are still inside the set of remaining points. So each point has a number associated to it. And I look for the one that has the biggest number. So is a point that has the biggest number of lines through it, still contained in the set. So if I remove that point, I kill all those lines. I get rid of all those lines. So this is the optimal way of getting to a cap set, right? Is to throw away this point. So I'm going to do that. I'm going to, well, there might be more than one with the largest number of lines. I choose one at random and throw it away, and then I move on. So at each stage, I find the point that I can remove to kill the most lines, throw it away, kill those lines, move on. So what do I get? So that's what's called the greedy cap set. And I want to know what I get. And I had a team of students over the summer look at that, and we proved this theorem that characterizes those greedy cap sets. So, by the way, this guy here is an example of a greedy cap set. You can show that, but it's not the only example. So what we found is that every time, so we did it on the computer. We just had the computer run and choose the points to throw away at random, following that rule, and many iterations, and we always ended up with a set of 2 to the n points. And to begin with, I didn't understand. I thought that we were going to get, sometimes we're going to get a bigger one, some going to get a smaller one, but no, it always ended up as being a set of 2 to the n points. And what happens is, when you do this procedure of finding the point with the most lines, you end up, to begin with, removing a hyperplane. So once we saw this, we were able to prove this. I mean, the paper is on the archive. Hopefully it's going to be published soon, but you can read it right now on the archive. When you do this procedure, you first remove a hyperplane. Now, remember, we're working over F3 to the n. So given a hyperplane, there is actually 2 hyperplanes which are parallel to that hyperplane. So you remove a hyperplane, there's 2 hyperplanes parallel to this hyperplane. And then you're going to repeat the procedure in each hyperplane. So in each of these 2 hyperplanes, you're going to remove a codimension 1 subspace of that hyperplane. So that's how you get the greedy cap set. You remove a hyperplane. In each of the 2 hyperplanes, you remove a hyperplane inside a hyperplane, and then you get 2 subsets of codimension now 2, and then you remove a subset of codimension 3 in either of them. I mean, 2 and 4, yeah, 2 and 2, yeah. So you do it like that. So it's a sort of this flags of subspaces, which is described here. So you the greedy cap set if only if it has a hyperplane. You remove the hyperplane so it doesn't meet H naught. H1, H2 are the parallel hyperplanes to H naught, and they are also greedy cap sets, so they miss a hyperplane. So in each Hi you remove a hyperplane, and so on recursively. And you can show that something that's obtained by this recursive procedure has 2 to the n elements. And this guy here, you're removing the hyperplane with the last coordinate is 2, and then you remove the hyperplane with the next to last coordinate is 2, and so on. So this one is pretty clearly a greedy cap set. So first we thought, well, we're going to get just those guys and linear transformations of those guys. But that's not true. So can we characterize the greedy cap? I mean, we characterize the greedy cap sets in this way, but what about the complete ones? Well, first I thought the complete ones would be these ones, but that's not true either. So I don't know. So the first question is, which ones are the complete greedy cap sets? So when you do this procedure, when do you get the complete set? I don't know. And the other question is, so later on I'll give you an example of a greedy cap set that is not complete. But there's this question, if it's not complete, it has a completion, which is going to be a bigger cap set. And how big is going to be this set? How many more points do you have to add? Does it require just a few points, or do you have, or are you going to get something much bigger? I don't know. I don't even have data for that because I only found not complete cap sets, for small. I mean, I could only find nice examples in the case of small q. So I don't really have a good feeling of what's going to happen. So how big are the completions of these greedy cap sets? Okay, so far? Any questions? All right, so that's the greedy cap sets. So next is quadrics. So remember, let's come back to here. And if I have a cap in Fq to the k, so a set with no 3 points on a line, on an Fq line, I get a cap set. So one way to construct, another way of constructing cap sets is to look at quadrics in three-dimensional space. So in three-dimensional space, you have two kinds of smooth quadrics. You have the hyperbolic quadrics, which contain lines, right? So they are fibered by lines. And there's the elliptic quadrics that looks like ellipsoids, which don't contain lines. So those gives you caps, and therefore they give you cap sets. So here's a theorem I can prove that if you have a known square in Fq, then this set is an elliptic quadric. And so it's a cap set. So that's easy. But the interesting part is that it is a complete cap set. So you cannot add any point to it and maintain the condition of... I mean, it's easy to prove that it's a complete cap. So if you take a point outside, there is a line to that, an Fq line to that point that meets the thing in 2 more points. But cap set is a stronger condition that there's no F3 line. And so that requires an extra argument. But it turns out it's not a very difficult argument, so I'm going to give you the proof. So, well, first of all, it's what I've already said. If it's an elliptic quadric, so it's a cap set. To show it's complete, take a point outside and consider this set here, the set of points in the space for which, so I have this point outside, and I look at the points in the space for which the third point on the line is on a quadric. And this turns out to be a quadric as well. So you just write down the equation. So you want to force the difference of those two vectors to be in the quadric, you just write down the quadratic equation, and you get a quadric. So Q prime is also a quadric, And if you find a, so what do you want to prove? You want to prove that the set is complete. So you want to show that through ABC, there is 2 points on the quadric which are, whose line passed through that ABC point. So you want to find a point in Q intersect Q prime. A point in Q intersect Q prime is going to give you a point, give you the pair of points. So through ABC. So these are two quadrics, and you want to find a point on the intersection of two quadrics. And first, well, if you have two quadrics in three-dimensional space and you intersect them, generically you get an elliptic curve. So I was very excited. I'm going to use elliptic curves. That's going to be cool. But it turns out that those particular two quadrics, they already meet at infinity in two conjugate lines. So you don't get an elliptic curve. You get a reducible curve, which is these two lines plus a conic. And then, you know, a conic has a point. So you use just the, you know, just by very simple algebraic geometry, you prove that this intersection of Q and Q prime have a rational point, and that's the, and that shows it is a complete quadric. And I've been going very fast, but I have a couple more things I wanted to say. So I'm going. I didn't. I don't have slides, but I can tell you about it. So I want to go back to the. Let me just go back to the slide, or maybe yeah. So let's look at this slide for a minute. So that's my quadric. And okay, so let me write down something. So I'm going to take, so the origin is in this quadric, right? So if you plug in x equals y equals 0, you get a point, right? X 0, 0, 0, right? X equals y equals 0, then the third quadrant is also 0. So I want to look at q minus 0, 0, 0. So q was a cap set. So this is also a cap set. And Q was complete. This is not complete. So this is not a complete cap set. A cap set, this is a cap set, but it's not complete. Okay, so let's remember that. And go back here a bit. Here, yes. So I was curious about complete greedy cap sets. And so just to, so my example is when Q is Q is 3, so F3 cubed can be identified with F3, what am I trying to do? Yeah, F3 cubed. Don't need to identify anything. So I'm working with, I want to work with F3 cubed. So the whole space has 27 elements. 2 cubed is 8. And this cap set, so the quadric has Q squared points. So the quadric has 9 points. Right? The quadric was the set of values of a function in x and y. So it has Q squared points. So that thing has 8 points when Q is 3. So it's a cap set with 8 points. And 8 is 2 cubed. And this is a greedy cap set. So that's the interesting thing, which is not obvious. I mean, it's not very difficult once you write down and you look for the missing hyperplanes. It is greedy. So you get an example of a greedy cap set that is not complete. So the initial guess that all the greedy cap set was complete is wrong. It gets completed by just adding 1 point because the quadric is complete. So the completion has 9 points. In this case, it's not very interesting because when in F3 cubed, the largest cap set has 9 points. So the quadric is an example. I don't know if it's the unique up to projectivities, but it is an example of a cap set of maximal size. So for q equals 3, for n equals 3, the maximal size is 9, and you have the greedy cap set as size 8, and you can to complete. If it's not, sometimes it's complete. So if you have this guy, it's complete, but that guy is not complete, and it gets completed with an extra point. So we know the value of the size of the maximal cap set up to 6 only, and which is quite interesting. There are some guesses for 7 and 8, but we don't know what's the size of the maximal cap set beyond 8. The case n equals 4 is there's a game called Set, which is a card game that you can play, you can buy it, and it's quite interesting. You learn some combinatorics with it, and it's based on this notion of cap sets or lines and stuff. And I think there's going to be a poster about this. So maybe if you want to know more about this game of Set, you should go bother the person presenting the poster. The largest cap set in dimension 4 has 20 points. So the greedy cap sets have 16 points. So there's a sort of a gap. I'm not sure if I know a greedy cap set whose completion has 20 points. But it's not. I cannot prove anything. It's just a question of maybe I didn't run the computer long enough. But I think I found greedy cap sets whose completion has 18 points, so from 16 to 18, but not up to 20. But so here's a challenge, maybe for the students who prepared the poster. They can look at that. We can do that with the cards, right? You can look for the cap sets just by playing with the cards. Find a greedy cap set with 16 points, for which the completion has 20 points. So I was asked to give this talk a day early, so maybe I can use that as an excuse that I've run out of material too soon. So I think it's pretty much what I wanted to say. So thank you.
Thank you very much, Filippo, for your nice talk. And are there any questions or comments for our speaker?
Thank you very much. It's very interesting. So this construction, this greedy stuff recalls me some construction about caps, like the doubling construction or something like you put a copy of your favorite guy in a hyperplane, and then in another hyperplane you take another copy, you join them. Clearly this is again a cap, perhaps say that the intersection is empty. So my question was, what about you say that you run some program in order to check whether the completion of this guy is 18, you said. So okay, but could you prove something in general? So if you take 2 quadrics for bigger Q, not for just 3 to the power 3, I guess. But did you get some results like I need at least this number of points to get?
I don't know. No, I don't. Yeah.
Okay.
Because sometimes the greedy cap sets are complete.
No, but for that example arising from a quadric.
Yeah. Quadric minus the origin.
Yes. Do you have something for general?
This one, I think, if you just take the origin out, because the quadric is complete, the only completion is to put
No. Just taking 2. Yeah, two quadrics, and then
So the case of conics, so the case in the plane, I can
Uh-huh.
do more, right? So I have examples with many conics, but in 3 space, I don't think I cannot put a second conic.
Okay.
Maybe in higher dimensional space I can, but in 3 space, I don't, I put one quadric, it's complete, so I cannot put anything else.
Yeah. I was thinking about in dimension 4. So in dimension 4, you take
tried,
two
yeah.
hyperplanes having this guy.
Yeah, that's a good question. I don't know what happens.
Okay, thanks a lot.
Hi. So, so your method of a greedy method, right? You start with something that's not, and you remove. You remove. Now, is it computationally too hard to actually try to enumerate via some? It reminds me like finding all cliques in a graph, but it's in this case is an higher
Enumerate
dimension.
all the greedy cap sets?
Yeah, enumerate by adding in any possible way until you can't anymore. Is it? Does it? For small cases, have you done, or is it possible to do?
Well, I haven't tried. So the students who are focusing. So this was part of this project with the 2 students, and they did a lot of computations with n equals 8, because we were trying to beat the. So the largest known cap set has 512 elements, but the greedy cap sets at 256. There's a big jump, and so I think there were too many possibilities to enumerate. So we tried, tens of thousands of iterations, and we were getting not so sometimes it was the completion had so you end up with something to size 256, you get something size 260, 270, 280. It didn't get beyond that, the completion. So we weren't getting very big cap sets.
Yes. Yeah, maybe.
So one question is, there's a very big group acting, so you want to take everything, modular the action of this group. So maybe that would simplify things a little bit, but we didn't do that. So maybe the way to answer your question would be to try and understand all the possibilities, modulo linear transformations. But maybe for small
for small n,
yes.
You could actually list them all to get some insight of which other kinds maybe exist, right?
Yeah, no, we haven't done that, but 3, 4 maybe is possible.
Yeah, okay.
Thank you.
Can I? Thank you, Felipe. Fantastic talk. My question is about the largest. Just to understand, in the theorem by Ellenberg and Gishwit, right? Do they actually provide a construction, or is just a non-constructive proof that you?
No, it's an upper bound. So you cannot have a cap set of the size 2.7 to the end.
That's right. But they cannot really give you.
So the best construction is this other work of Tyrrell, and also the which is where is it?
Yeah, there.
2.27. So these are explicit.
These are explicit.
Explicit. So what you do is you construct a cap set for a specific n. You construct one example, and then you take Cartesian products. So if you have a cap set C and then C to the n. So if you have a cap and then you have, you know what the size of
you can build the actual.
Yeah. But the best examples always give you something. So there's a big gap, right, between 2.2 and 2.7.
Right.
Yeah, but the upper bound is a proof by contradiction, right? So you assume that there's something bigger, and then you show that it cannot.
Yeah, so there's non-construction.
There's no.
No, because there are upper bounds that you can actually provide the construction, but in this case, it's by contradiction. So.
Yeah.
Thank you. Thank you for the talk.
Okay. Are there any more questions? Okay, if not, let's thank our speaker again. Thank you so much. Now we have a coffee break.
Thank you, Maria.
Okay. This is the test. People hear me? I'm saying something. Is it okay?
Okay. Welcome back, everybody. It is my pleasure to introduce the first speaker of this session, Betul Turgay, who is going to talk about a unified approach to the algebraic structure of quasi-cyclic codes. So, please.
Thank you so much. Good morning, everyone. And today I would like to speak about unified approach to the algebraic structure of quasi-cyclic codes. But before that, I thank you very much that you let me be here. And I thank to the TÜBİTAK, which is the Turkish Scientific and Technological Research Council. They support us in every way. Okay, this is my brief outline, introduction, and after that, I'll speak about representation of the quasi-cyclic codes, and then spectral analysis, paired check matrix, and then quasi-cyclic codes over extension fields, and then a generator matrix using Grosvenor basis. After that, last of all, relationship between the spectral and the concatenated structure. Now let's refresh our minds. What is a cyclic code? It's a code that is closed under one bit of shift, but quasi-cyclic code, it's closed under blocks of shift. The length of the block is M, and there are L many blocks here. Now let's see how we represent this quasi-cyclic code word. We write the code word, and we take this one block, we make it a row, the other block, other row, and then we have a matrix, and we take this column, we make it a polynomial. These are the coefficients of the polynomial. Now, what does that mean we make L shift? It means that we multiply this polynomial vector by x. How? This is the coefficient of x to the power m minus 1. If we multiply by x, this becomes x to the power m, which is 1. So this is quite shuffling. I'm sorry. I don't know what to do. Anyway, this becomes the constant term. It becomes here. And this becomes the second term. Now the last row becomes first row. The first row becomes second row. This way we shift. Okay. Now, yes, shifting this code word by L positions means this, in fact. We just multiply the polynomial vector by x, modulo x to the power m minus 1. Okay. We can consider a quasi-cyclic code as the Fq(x) over x to the power m minus 1 module of the algebra, Fq(x) over x to the power m minus 1 to the power L. This is one way. For practical purposes, we call this part, where am I? Oh, sorry. Oh. How do I go to the first part? I skipped to the last part. That's funny. Oh, sorry. How did I manage to do this? I don't know. All right. Yes, for practical purposes, we let this. Okay, this is R, and this is I. We call this way. Now, let's see how we produce a Grosvenor basis. Lally and Fitzpatrick, they proved that every quasi-cyclic code has a reduced Grosvenor basis. And this basis can be represented by an L by L polynomial matrix. This is a special matrix. As you see, this is upper triangular. And the diagonals, they all divide x to the power m minus 1. And if one of them is x to the power m minus 1 itself, then the other terms are 0 here in this row. Moreover, the degree of the upper terms, they are all less than the degree of the diagonal for each diagonal. Okay. Yes, these are the rules. We call this matrix Grosvenor basis of the quasi-cyclic code C. And Semenov and Trifonov spectral analysis. What's this? We use eigenthings to make some analysis here. Semenov and Trifonov gives us the following definitions of the eigenvalues in our context. Now, they are a little bit different than the linear algebra. Here, we consider a polynomial matrix. We find the determinant, we find the roots of the determinant, and these are our eigenvalues. And let's pick an eigenvalue. We plug it here. Then, if we solve this equation, then we get the eigenspace. These are the eigenvectors. This eigenspace corresponding to lambda I, of course. In our case, we calculate this determinant, G tilde, and we find the eigenvalues. If this is, no, we are going to produce a parity check matrix. How do we do this? We pick an eigenvalue, and we find the basis of the eigenspace, we take the transpose, we stack them vertically. Now we have this matrix Vi. We construct another matrix using the eigenvalues. We take the powers of them until m-1, and then we take Kronecker product with Vi. Then we stack again these HIs. Now comes our paired check matrix. This is our paired check matrix. Now, a quasi-cyclic code can have several different paired check matrices, but if we are given a paired check matrix, then the quasi-cyclic code that has this matrix is unique. And let's call this matrix C hat. C unique linear code having this paired check matrix. Now, how to find a generator matrix using Grosvenor basis? We can find a generator matrix with the information above, but for this purpose, we need this subspace, FQR subspace, generated by these things, v dot g tilde lambda, for specific lambda. The dual of this subspace is v lambda perp. This is the eigenspace of the code with respect to the eigenvalue lambda. All right, how do we find G hat? We pick subcollection of the eigenvalues of C, which are not making 0. If we evaluate at G tilde, this is not 0. And let's say Gij, generator matrix of the code W, this one. We defined before, this is the generator. And we construct the following matrix using these matrices and eigenvalues, according to Shimazul, thanks to him. This is G hat. Now, the following theorem is very helpful for us to study more properties. The code over FQR in the extension field with the generator matrix G hat is the subcode of C hat. In the proof, the idea is correct, but there's a mistake. After the correction of this mistake, we gave the full generator matrix of the code C hat. Now, how do we find the full generator matrix? We use the eigenvalues of C and C perp. Let's say this is the set of eigenvalues for C. Let's say this one the set of eigenvalues of C perp. We write this G bar using these. First, we use these ones and take the powers, and then we take the Kronecker product with V1. We use these lambdas here. And the idea of proof is simple, but the proof is quite messy and long. We just show H hat times G bar transpose is 0 for this proof. All right. Now, the relationship as to the relationship between the spectral and concatenated structure, we use these sets, the set of eigenvalues of C, and the set of E perp is the set of roots of this reciprocal. But we need two more things. This G tilde lambda should not be identity. If it's identity, then we get empty eigenspace. And moreover, if this G tilde lambda is 0, we get the full space for the eigenspace. We don't want these. Ezerman and his colleagues show that if this is the set of eigenvalues, then the code C tilde lambda I contains the constituent as the set spanned by the rows of G tilde lambda I. And this is a subfield subcode. Okay, now I think sure product comes, yes. Let's say C and D are two quasi-cyclic codes. Their sure product is defined as C star D, which is just spanned by the set C star D, where C is from this one and D is from this one. And this is the star this sure product. If this is compound-wise product, just as everyone knows. Now let's define the describing set. It's funny, define the describing set. If the set of eigenvalues of the dual of a quasi-cyclic code is this way, then the describing set is the powers of these eigenvalues. Here it's minus I1 up to I minus IR. Now, let's see some theorems. We use spectral theory to prove the following theorems. If we have two quasi-cyclic codes, and they are the same length, then C star D is also a quasi-cyclic code. Moreover, the index of this Schur product is the least common multiple of the indices of these codes. And another theorem, if J1 and J2 are describing sets of the quasi-cyclic codes, then the describing set of the Schur product is J1 plus J2. This is for the Minkowski sum. And I think I'm done. Do I have time? I think I have time, little time. I would like to draw what I did. Now, in fact, not I did. Many people did, and I just explained. This is our code, and we use eigenvalues to produce a parity check matrix, and we call the code which has this parity check matrix as C hat. Now, this is in the extension field, and this C is in the base field. This C is the subfield subcode of this C hat. Now, we produce another generator matrix. We use a subcollection of the eigenvalues. Oh, my writing is terrible, I'm sorry. And if we find the code, let's say curly C, that has the generator matrix as G hat, now these are related. This is the subcode of this one. This is the subcode of this one. And we find, where did we find it? Let me see. This one. I'm sorry. This one. This G bar is the full generator matrix of this code. Full generator matrix. So this is quite a summary, I think. And let me finish my talk with showing the references. These are my references. Thank you very much for listening. Do you have any questions?
Thank you very much for your talk. Are there any questions for our speaker? Yeah.
Actually, I want to ask the question, like on slide 5, you talk about Grosvenor basis.
Oh, so, where are they?
On the slide 5th.
Okay.
So what is the connection between the quasi-cyclic code you talked earlier and the Grosvenor basis?
Yes, you're right.
But on slide 5th.
Wait, how do I find it? This one?
5.
5. Okay. This is quite longer process. If you use Grosvenor basis to construct this matrix, but maybe we can talk in free discussion or somewhere else.
Okay, and also, yeah, sure. And also one more question on slide 15.
15. Oh, no.
Yeah. Yes. So, like, what is xi here? Like, I am not getting, like, what is xi?
This is just an expression. Lambda, xi, it doesn't matter. It's an eigenvalue. These are the eigenvalues, set of eigenvalues of the dual of the quasi-cyclic code.
Okay, okay, thanks.
Oh, you're welcome.
Any other question?
I understood why this shuffles. I'm so sorry that I bothered you so much with my shuffle. Anyway.
If not, then let's thank our speaker again.
Okay.
Now we have 7 minutes of break.
Oh, voilà.
Sorry.
No, it's my problem. This shuffles.
No problem.
I should have arranged.
Okay, thank you.
Try my presentation. No. Okay.
It's not working. All right.
Okay, so let's proceed with this session, and it is my pleasure to introduce Zainal Caracas, who is going to talk about optimum distance cyclic H-orbit full flag codes. Please.
Yeah, thank you, Maria. And I want to start my presentation with thanking the scientific committee and organizing committee of this conference for having us and giving us this opportunity to present our works. And I also wanted to thank TÜBİTAK, a Turkish scientific organization, for supporting me in this work. And my work's title is Optimum Distance Cyclic H-orbit Full Flag Codes. This work is a joint work with Ferruh Özbudak and Buket Özkaya. And I'm going to give you our, firstly, the necessity backgrounds and definitions, and then I'm going to give you our main works, results. And in the third section, I will present you the actual results after magma search, and I'm going to finish my presentation with references. And as you all know that, like over here, Q is a power prime and the power of prime number, and Fqn is the final field of order Q to n. Over here, up to one point, we'll consider n to be any integer greater than or equal to 1. And the extension field over here can be viewed as an n-dimensional vector space over Fq. And the parameters will be in almost every pages. So then I will tell them once, so then you can assume that it's acceptable for all. Over here, n is an integer, any integer greater than or equal to 2, and we are picking a number between 1 and n minus 1 r to make it an index for our ti's, and putting them into a vector, giving us the type vector t over here, and flag is composed of these tr elements. Over here, we name a flag of type t in Fq to n over Fq. Is defined as nested subspaces. Over here, strictly less than, including the other ones. And each element has ti dimension, as you see. And for the flag, we use this notation. And by the ambient space of flags of type t in Fq to n over Fq, we mean the collection of S consisting of all flags of type t in Fqn over Fq. And by flag distance, let's consider two distinct flags over here, F1 and F2. And the distance between them is nothing but the summation over I of their the subspace distance of their corresponding elements, UTI and VTI. Sorry for typing over here. It was supposed to be R. And the subspace distance, as you most know, is the summation of their dimensions, the elements, and minus 2 times the dimension of their intersection over here. And by minimum flag distance for our code, to make it valuable as a code, we have a flag code of type T in Fq to n over Fq. We mean a subset of this ambient space S. And with respect to this distance, we have our code C, and that distance is the minimum of these pairwise flag distance calculations results. And they must be, of course, distinct. And the minimum admissible distance is the number D. That, like, for that, having that as a flag distance, our code C of type T in Fq to n over Fq existed. And I mean, if this type vector includes all the numbers between 1 and n minus 1, all of them, then our flag is called as full, and our code is full flag code, becomes full flag code in Fq to n over Fq. And here there is an upper bound for the full flag distance according to the characterization of n. If n is even, it might be at most n or n squared over 2, and if n is odd, it might be at most n squared minus 1 over 2. After this moment, I'm gonna consider n to be even for our works, for our constructions, actually. And also we are interested in this bound over here with saying optimum distance. It means that like our code reaches this upper bound, and having full flag over here distincts our work with the previous ones in the literature. Over here, I'm gonna also emphasize them shortly. Over here, like in order to tell our results, I need to say that first we use the vectors, n-dimensional vector space over Fq and the extension field. We consider a k-dimensional subspace of this vector space. Actually, this U is element of vector space. So small typing mistake over here. Sorry for that. And we are having a non-zero element alpha of this extension field, and we are having U alphas as an element of k-dimensional Grossmanian. And in this way, Fq to n star acts on this Grossmanian, and hence it allows us to build orbits of this multiplicative action. And over here, we can define the cyclic orbit code generated by U as U alphas over here. And the stabilizer of it is given as alphas, non-zero alphas of Fqn, satisfying this equality over here. And the code orbit U has cardinality Q to n minus 1 over Q to m minus 1, if and only if the stabilizer is equal to Fqm for some divisor of n. From now on, as I said, we will consider n to be even. And over here, we have, when we are given a flag of type T for any type, I mean, in order to explain what cyclic orbit flag code is, we are having any type vector, and then we are having any non-zero element of Fqn, this extension field, and we multiply all the elements of this flag, and with respect to, again, flag distance, it gives us the cyclic orbit flag code. And we have, in order to understand what we did, I need to give lastly this definition. If our cyclic h-orbit flag code reaches the maximum size, so we call it maximal, and over here its size is q to n plus 1 actually. Otherwise, it's going to be shortened by some capital N over here, or Z here is element of, actually primitive element of Fq and star. You can take it like that. And the cardinality of C over here is the capital N. And in this case, we call the C is, I mean, from this point of view of size, it reached its best possible size. Moreover, optimum distance of C is acceptable when it reaches when it has the minimum distance as the biggest possible, as I gave it earlier. This is our main theorem, and it says that having a Fq as a finite field over here and putting C, small c, is equal to Z over Qn minus 1 over n. And our flag is given by this. You see it's a full flag. It contains all the elements from 1 to n minus 1. And it's a flag under Fq to n. Then our the collection of this C, the collection of multiplication of powers of C's with this flag is an optimum distance cyclic H-orbit full flag code. While calculating the size of the code, the value of n is crucial, and it's exactly q to n over 2 plus 1 over m. Over here, our m is maximum of 2 to k, where 2 to k divides q over n plus 1, but 2 to k plus 1 doesn't divide q to n over 2 plus 1. It takes this m number as a denominator, so it makes it become best possible, not maximal, when q is odd characteristic, when our base field is odd characteristic. But when it's even characteristic, it reaches the exact the maximum possible option, which is maximal. We name that as in definition 8. And in order to make it something more understandable, I put an example over here. And over here, we consider n to be 6. And W over here, omega, is the generator element of primitive element of Fq6 star. And raising it to two different i's, like I1 and I2, gives us alpha 1 and alpha 2 over here. And we here claim that the multiplication of this multiplication Fq cube with this alpha 1 and alpha 2 intersects trivially. And here it gives us, for example, two different flags over here, alpha 1f and alpha 2f. We claim that its minimum distance is flag distance is it's 18, which is actually n squared over 2, as we promised earlier. Clearly, we have over here Fq cube star is generated by omega to q cube plus 1. And for a contradiction, we can assume the opposite. What if they had something more in the intersection? Then it would be possible to have this equality for some I and j's, but this implies that omega 2 I1 times omega 2 q cube plus 1i is equal to omega 2 I2 times omega 2 q cube plus 1j. And therefore, it would be possible for q cube plus 1 divides I1 and I2, which is a contradiction, as it's not in the Fq cube star. The division is not in Fq cube star, so they intersect trivially. So we have, for the one-dimensional vectors subspaces over here, we have the subspace distance 2, and for the 2 to 4, which is most possible, and so on. It ends up with all this, and when we sum up them, we reach the promised distance. Any question about this example or like earlier explanation? Okay, then I will give you two consecutive theorems that like shows how it becomes maximal and how it becomes best possible over here. When q is 2 over here, we have n6, and let C0 be the flag code defined above in the just like the example. But like we are after example, if we take q to be 2, then the flag distance 18, and in particular over here C0 is optimum distance with respect to its flag distance, and its cardinality is maximal. But otherwise, if it's odd characteristic, it gives us some sub-cases in each time, and it goes according to Q. Over here, for example, if Q plus 1 is equal to 2, then our M over here is 2, and our cardinality is Q plus 1 over 2. And if Q plus 1 over 2 for mod 8, then our A is to be equal to omega 2 4 times Q cube minus 1, which is a generator of our H cyclic subgroup. And over here, M becomes 4, and this capital N is the best possible size for this case. And Q cube plus 1, when Q cube plus 1 is 0 mod 4, then it becomes Q cube plus 1 over 8. So these sizes are best possible ones. And next, I want to give you some actual results after magma search. According to our results, we have two conjectures over here. One is solved partly by us. The other part of the first conjecture and the second conjecture is still on. And for example, our first conjecture says that, as you see, when Q is when characteristic even, look at the even characteristics, and when N is 0 mod 4, just like this and just like this, our distinct flag is uniquely determined. As you see, the number of distinct flags is 1. But when N is 2 mod 4, just like here and just like here, the number of distinct flags in our code becomes Q to N over 2 plus Q to N over 2 minus 1, blah, blah, and 1. So this is our conjecture 1, as you see. And for the first case, for the uniquely determined case, we solved it and created this theorem and proved it in our work. I'm not going to give the proof here, but if someone is interested, we can discuss later. Over here, let Q be even and H to be FQ to 4 stars, any cyclic subgroup. And over here, H is generated by Z to Q square minus 1, and its cardinality is Q square plus 1. And over here, as you see, we took a very special, very small parameter for N to be 4. And here, Z is primitive element of FQ to 4 star. And our U is the FQ linear subspace of this FQ4, such that the cardinality of U is Q square. And taking two distinct elements of H ends up with the trivially intersected alpha 1U and alpha 2Us. Otherwise, if they are not distinct, so then they are not trivially intersected over here, and our U is FQ square linear. This is our last result for this work. And the other conjecture, second conjecture over here, says that from the, after our results, we presented it, when n is 4 and q is odd, it goes like that. Our number of distinct flags is still q squared plus 1. This is our second conjecture, but it needs to be proven shortly. I think pretty much that's all. These are, let me talk about this part as well. All this work is a generalization of cyclic subspaces to the flag codes, and it reaches optimum distance. It is full flag, and it has maximal size. And these are my references. Thank you for listening to me. And if you have any question.
Thank you. Thank you for your talk. Are there questions?
I have just one question, really does not connect it directly, but if you have a flag, you can look at the duals, so you have another flag.
Yeah.
And you are studying something like equivalent flags, no? Because you have a code, you multiply by a non-zero vector, you have an equivalent code.
Yeah.
So, for example, you could have a flag, you take the duals, and then the duals go back to a equivalent flag.
Yeah.
And you know the vector.
Yeah.
So, in this case, do you think that could help somehow to do your computations, or like, you have a flag with some structure?
Yeah. For this, we presented our work up to this moment, and for the equivalency, we haven't. For the near future, we're gonna also search the equivalents, like we did in our previous works, like monomial equivalence or permutational equivalence, or like general linear automorphism group equivalence. We haven't looked at that, but like maybe next work we will continue on that. Thank you for your comment.
Any other question? Okay, if not, let's thank our speaker again.
Thank you very much. Thank you for listening to that.
We start again in 2 minutes. Okay, so here it comes the last speaker of this session, Akanksha, who is going to talk about generalizations of cyclic codes over product rings. Please.
Hello. So first of all, I would like to thank the organizers for giving us the opportunity to present our work. So my name is Akanksha. I'm a research scholar in the Department of Mathematics, IIT Delhi, and I'm going to present joint work with Ritumuni Sharma. The title of my presentation is Generalizations of Cyclic Codes over Product Rings. So this is the outline of my presentation. I'll start with the introduction. So these are just basics of coding theory, but I'll cover it for the sake of completion. So throughout this presentation, Fq represents the finite field of cardinality Q, where Q is a prime power, and the humming distance between two vectors of equal length is the number of positions at which they vary. And the distance of a code is the minimum distance between two distinct code words. And a linear code of length n and dimension k over Fq is a k-dimensional subspace of n-dimensional vector space Fqn. And every linear code satisfies this singleton bound. And the code that achieves this bound is called MDS code. And a linear code is said to be cyclic if it is closed under left or right cyclic shift. And it is called lambda consa-cyclic if it is closed under this linear transformation where lambda is non-zero element in Fq. And for a vector A in Fqn, it is said to be a polycyclic if it is closed under this linear transformation. Note that these definitions are combinatorial, and consa-cyclic codes are generalization of cyclic codes, and polycyclic codes are generalization of consa-cyclic codes. But these combinatorial definitions have algebraic analogs as well, which is captured here. So for that, we define this map phi from Fqn to this quotient ring, where we identify a tuple by this polynomial. And with the help of this Fq vector space isomorphism, we can see that a code over Fq of length n is cyclic if and only phi c is an ideal in this quotient ring. Similarly, if the same map is defined from Fqn to this quotient ring, we can see that a code over Fq of length n is lambda consa-cyclic if and only phi c is an ideal in this quotient ring. And a similar result holds for polycyclic codes. So when the same map defined from Fqn to this quotient ring gives us that C is an A polycyclic code if and only if phi c is an ideal in this quotient. So similarly, first of all, we define codes over fields. So similar to that concept, codes over rings also exist. So for a finite ring, commutative ring with unity, linear code is nothing but an R submodule of Rn. And the definition given for cyclic, consa-cyclic, and polycyclic code also hold the combinatorial one and the algebraic one, both. And by abuse of notation, we'll identify C by phi c. So they can be used interchangeably. So an inner product is nothing but a non-degenerate bilinear form. And the standard example for that is this Euclidean inner product. So that is defined for two vectors C and D in Rn like this. And since we have an inner product, we can talk about this Euclidean dual. So the Euclidean dual is collection of all those elements which have inner product 0 with every code word. So what do we mean by a product ring? So the underlying set of a product ring is FQL, and the addition and multiplication are given component-wise. So now we are ready to do the literature survey. So in 2018, Gao and Wang studied consa-cyclic codes over this ring. Note that if you see this ring, this is actually isomorphic to a product ring FQ2. And the results in this article can be generalized for polycyclic codes, a larger class. Further, Fortutabu and others studied polycyclic codes over an arbitrary finite chain ring. And later, few authors have studied polycyclic codes, consa-cyclic codes, and cyclic codes over various non-chain rings, and these non-chain rings were isomorphic to a particular product ring. And they gave results regarding decomposition, duality, and generator polynomial of these codes. And polycyclic codes have been studied as invariant spaces by Xi and others. This is in different direction, one can see that. And in 2021, Slam and others studied cyclic codes over a class of non-chain rings. And if we see this article, this class is actually isomorphic to a class of product rings. In fact, this is a subset of class of product rings, and it is a proper subset. And polycyclic codes associated with trinomials have been studied by Aydin and others, and they have presented many open problems. Further, Key had studied polycyclic codes over this ring, and note that this ring is again isomorphic to a product ring FQ2. And he has constructed many optimal MDS and almost MDS codes. And in 2023, Bhardwaj and Raka has studied constant cyclic codes over a wide class of rings. So by wide class of rings, I mean that they have studied constant cyclic codes over Fq(x1, x2, xk, quotient by F1, x1 up to on and on Fk, xk, where each Fi, xi splits over Fq into distinct linear factors. So this type of ring is again isomorphic to a product ring, which we'll see later. And it is also a subclass of product rings, and it is also a proper subclass. So from literature survey, the aim and problem is almost clear. So we intend to study polycyclic codes over product rings, and this work generalizes the works done in previously. And after that, we have defined a gray map with the aim to obtain some optimal and MDS codes. So let us start with the results. So firstly, we characterize the family of rings on which we want to study polycyclic codes. So for that, we have this theorem. So for a polynomial over Fq and a natural number, we have that this quotient ring, Fqx quotient by Fx, is isomorphic to a product ring if and only if this Fx splits over Fq into distinct linear factors. And considering codes over rings of this form is actually a particular case of considering codes over a product ring. Since if we consider a ring of this form where Fx splits over Fq into distinct linear factors, it is always isomorphic to a product ring. But there are product rings for which such a form cannot be found or does not exist. For example, if we consider F P1, P2, where P1 and P2 are primes and P2 exceeds P1, then this ring cannot be realized as this. So this result can be extended for multiple variable case as well. So this ring Fq(x1, x2, xk) quotient by this is isomorphic to a product ring if and only if each Fi, xi splits over Fq into distinct linear factors. And this was the same ring that was considered by Bhardwaj and Raka. So further, now we'll see that these rings have property that they have Fq basis consisting of orthogonal idempotents having some 1. So an Fq algebra, a commutative finite Fq algebra, is isomorphic to a product ring if and only if it has a basis consisting of orthogonal idempotents and having some 1. And such a basis is very important because it gives us a way to decompose R. So if R is isomorphic to FQL, we'll have such a basis and we can decompose R like this, and this component will be, these two components will be equal, and R will have this decomposition. So let's fix some notations. So throughout this presentation, this mathcal R represents the product ring, and since it is isomorphic to product ring, we'll have a basis of this form, a nice basis, and we can actually write every element A of R uniquely in this manner. And because of this representation, we can define ith canonical projection. We can extend it to Rn and denote it by pi I tilde. So due to this, we'll have a way to decompose every R submodule of Rn into Fq linear vector spaces of Fqn, and this is captured in this theorem. So for a subset C of Rn, we denote by Ci, this pi I tilde C. Then we have that an R submodule of Rn. Then C is an R submodule of Rn if and only if each Cj is Fq subspace of Fqn, and C is equal to the sum of this. And every R submodule of Rn can be written as sum of this uniquely, as written here. So it can be decomposed in this manner. Let's fix some more notations. So for a vector A bar in Rn, each Ai is an element in R, and then it can be written uniquely like this. And we define A subscript j as this. So every A bar can be written as sum of this. And with the help of this A bar and A superscript j, we can link the structure of C and Ci's, that is here in this theorem. So let C be an A polycyclic code and it is an Fq decomposition of C. Then this A bar can be written as sum of this, and C is an A bar polycyclic code over R if and only if each Ci is this A subscript I polycyclic code over Fq. And not only that, we can also get a generator polynomial for C as well. So let C be an A bar polycyclic code over Fq, and this is the decomposition of C. Then there exist these GIs in this quotient ring such that this sum, that is G bar x, the sum of these EIGIX, serves as a generator polynomial for C. Not only that, if we have a generator polynomial for C, that is G bar x, we can actually decompose this and get generator polynomial for CIs. So further, Note that it is well known that the Euclidean dual of a polycyclic code may not be polycyclic. So to tackle this, in 2016, Alamuddin defined a bilinear form over Fq that we extend for Fql. So for a polynomial in Rx, we define this bilinear form from this to mathcal R. It is defined in this manner. If we have these two polynomials, then the bilinear form, so the product is nothing but the evaluation at 0 of this remainder, which we get when we divide this product by x raised to power n minus a bar x. So note that when we have this constant term of this polynomial unit in R, then this bilinear form is an inner product. So since we have an inner product, we can define its dual. So first of all, the bilinear form defined in this definition is called annihilator product, and the dual of a polycyclic code with respect to this is called annihilator dual, and this is represented by this C naught. So C naught is the collection of all those elements in the quotient which have inner product 0 with every code word. And also, since C can be realized as an ideal, so this is nothing but annihilator of the ideal. So it is collection of all those elements for which the product is 0. So they are actually related, this C naught and annihilator of C. So it is here. So for an A polycyclic code, we see that if this A naught is unit, then we know that bilinear form is an inner product, and in that case C naught exists, and C naught is nothing but equal to annihilator of C. So we have seen that the dual of polycyclic code do not carry the same structure, but they carry the structure of sequential code. So for that we define this. So for a vector alpha bar in Rn, an R linear code is sequential if it is closed under this map. So here it is Euclidean inner product. So as we have given result with the help of decomposition for polycyclic code, we can get the same result for sequential codes. So let C be an R linear code of length n, and A bar is a vector in Rn, then C is A bar sequential over R if and only if each Ci is A subscript I sequential over Fq. So this was proved by Lopez-Permouth. So a linear code C over Fq is A polycyclic if and only if its Euclidean dual is A sequential. And then this result can be extended for Fql, that means mathcal R. So an R linear code is A bar polycyclic if and only if its Euclidean dual is A bar sequential over Fq. So now we'll actually relate the annihilator dual and Euclidean dual. So for an R linear A bar polycyclic code, its annihilator dual is equal to the Euclidean dual of C dot A, where A is the gram matrix of this annihilator inner product. And with the help of this, we get that taking annihilator dual twice gives us the code back. Not only that, if we have an A bar polycyclic code over R and we know the Fq decomposition of this, then we can give the Fq decomposition of its annihilator dual as well. So with the help of these results, we give the main result of our article. So for an element A bar in Rn, an R linear A bar polycyclic code is so C is an A bar polycyclic code if and only if its annihilator dual, that is C naught, it is also A bar polycyclic. That means both C and C naught carry the same structure. So the proof is simple now. So if we have an A bar polycyclic code over R, then we have an Fq decomposition of this, and then we know its Fq decomposition. Then with the help of the previous result, we know the Fq decomposition of C naught, and Ci and Ci naught carry the same structure because of this result. So Ci naught is also AI polycyclic, and again using the decomposition result, we have that C naught is also A bar polycyclic. So this is the main result. Again, to obtain some optimal codes, we define a gray map. So gray map has been defined in this manner, where M comes from an L cross L invertible matrix. So with the help of this gray map, we have found some optimal codes that are here. And now our aim was also to construct some quantum codes. So for that, we have proved these two results. So this is the gray map that we defined above. So for an A bar polycyclic code over R, if we fix each AI, each coefficient in this polynomial to be a repetitive one, then we get that psi of C dot A is nothing but psi of C dot A bar. And for a particular A bar x, where A bar x is a constant polynomial and A naught is a repetitive one, then we get that the minimum distance of psi C and minimum distance of psi C dot A bar are same. And with the help of this Euclidean CSS construction, which is a gateway to construct quantum codes with the help of Euclidean dual containing codes, we give the construction of quantum codes, which is captured in this theorem. So if we have an A bar polycyclic code, and where A bar x is a constant polynomial and it is of this form, and we have in the gray map the matrices that appear are of this form, then we get that there exists quantum code with this parameter, where d is the mean distance of psi c. This is the table that is consisting of quantum codes that we were able to construct. So these results can be found in this article. Thank you.
Thank you. Thank you very much for your talk. Are there any questions? Okay, if not, let's thank our speaker again and all the speakers of this session.
So guys, just one quick announcement. And again, like yesterday, if you want to follow a group to go for lunch somewhere,